Hello and welcome to Bytewise. This is the channel where we design and build projects using electronics and computing. We'll usually be developing working practical projects that can demonstrate some of the basics of electronic and computing design. Sometimes we'll throw in some web design too. Longer projects will be split across more than one video into a modular incremental design and build process. We'll be using graphics tools to explore the technology, hopefully making things clear and easy to follow. These days, building often means coding. We'll be using the Arduino IDE as a standard to develop in C++. Some projects will include other languages like HTML, CSS, and JavaScript. We'll also be talking about concepts like AJAX, WebSockets, and the Internet of Things. We'll walk through code with the focus on concepts and functionality rather than the detail of syntax and semantics. In the future, we'll look at providing PCBs and kits to accompany build videos. Today on Bytewise, we're starting our first project. This will be what we're calling a 21st Century Timeswitch, taking some familiar functionality and using new technology to update it. The hardware build is rated easy. There are only a handful of components and the project can easily be built using generic circuit boards. Configuration is rated moderate because we'll need to add the ESP8266 processor and all of its supporting libraries to the standard Arduino IDE in order to load our software. Software and concepts combine several different languages as well as the basics of real-time systems. For this reason, we've rated it challenging. Time switches have been around for a long while. Most people will have seen or used the two most familiar types, rotary electromechanical and electronic. But these designs have been static for years and lack modern features. So what would a 21st century time switch look like? What would it do differently? The most important feature is connectivity. The existing devices just sit there quietly on the wall without any connection to the outside world. Just how useful would it be to be able to control the device remotely, changing settings and turning controlled equipment on and off without having to be physically next to the time switch? This functionality might be available with proprietary Wi-Fi switches and home assistants, but they can be expensive. Currently, time switches also lack intelligence. That's a given with the rotary dial devices, but even the electronic ones lack basic features like daylight savings time, interconnectivity with other devices, and more complex time references like sunrise and sunset. There's also a question of accuracy. The present devices are intended for independent operation over periods of weeks and months, but often lack accuracy of timing over that period. So, let's fix all of those issues. For our connectivity, we'll be using the versatile ESP8266 transceiver microcontroller. If you aren't familiar with this chip, it's an incredibly powerful device. Costing less than $1, the chip provides both a microcontroller computer and various built-in communication options. The spec includes Wi-Fi, Arduino-compatible coding in C++, a web server, multiple inter-device options including Universal Data Protocol, and the ability to operate in two different Wi-Fi modes. We're not going to use the chip by itself though. There are dozens of ESP modules available, and these place the chip and its supporting circuitry into a more usable format. The smallest and most basic module is the ESP01 and its slightly updated sibling, the ESP01S. The S gets us a different setup for the onboard LEDs and 1 MB of flash memory instead of 512K. This project will run happily on either of those devices. Let's take a quick tour. These are the 8 pins that we'll use to connect the device. This is the ESP8266 processor. This is the 512K flash RAM. This is the timing crystal. The remaining components are the LEDs and the resistors that support them. The 8 pins break down as 2 for power, and VCC is 3.3 volts, 2 for transmit and receive of serial data, 1 to enable the chip and 1 to reset it, and that leaves the 2 exposed GPIO pins. The dedicated pin 2 and GPIO 0, which controls whether the chip is running or waiting for a new program to be flashed. Let's put our basic circuit together. We need a module that will enable connection to a USB port, and this CP2102 device does that. Helpfully, it also provides a 3.3 volt power supply that we can use. We'll start by connecting power. Next, we'll add the serial data connection TX and RX. Note that TX from the CP2102 connects to RX on the ESP01. We'll also connect the enable pin permanently to VCC. We'll need a reset button to load programs to the ESP01, and that connects to ground. No pull-up resistor is necessary. A further push button connects GPIO 0 to ground when we want to flash the device. We will also use this to provide a manual override to the time switch later. We can stop here and simply connect an LED and resistor between GPIO 2 and ground to be able to undertake the next steps of configuration and coding. For completeness though, we'll show the entire circuit, adding a transistor and resistors to invert the output of the ESP8266 and convert it to 5 volts before feeding it to a relay module. These relay modules vary. They usually have a built-in transistor driver and sometimes incorporate an opto isolator. So this is our complete circuit. Next, we'll put it together on a piece of general purpose perforated circuit board. This will be the design that we're working to. We're now going to configure the Arduino IDE for the ESP8266. The first step is to download the Arduino IDE if you don't already have it. For the Windows environment, the first 3 options on this list should all work, and the one to choose will depend on the configuration of your desktop. There's an option to make a donation, and other than that, the installation is very straightforward. We need to set up the boards manager. The first step is to enter the package URL into the preferences screen. It'll take a few seconds to load this configuration package. Once that's been done, you can go into the boards manager, search for ESP8266 and install the package. I've found that version 2.5.0 is the latest version that works without problems, and I think that's because of the firmware version that's installed on my boards. Now you can select the generic ESP8266 module board type and adjust the parameters. I've found that the default parameters work well. It's possible to increase the upload speed to 256,000 to make downloading faster, and if you have an ESP01S, you can increase the flash size to 1 megabyte. The last thing to do is to install the WebSockets library that we'll be using later. Select Manage Libraries to search for WebSockets and install the most recent version of the WebSockets library by Marcus Sattler. To test the construction of a newly built project, it's a good idea to run a simple program that's known to work. We're using the standard Arduino blink program, adding in output to the serial port. I've altered the blink pattern into 2 short flashes to make something more distinctive. You can find the blink program under File, Examples, 01 Basics, Blink. Putting the board into flash mode requires holding down the flash button whilst pressing the reset button. The flash button needs to remain pressed for a couple of seconds as the module reboots. Flash mode allows us to download the program. The download is started by clicking on the download button in the toolbar of the Arduino IDE. In some versions, it's necessary to reset the board again after download. You can examine the serial output by selecting Tools, Serial Monitor, or clicking on the magnifying glass icon. The transmission rate must match the rate set in the program in serial.begin. The default rate for the ESP8266 is 74,880 baud. The board I'm using here is an ESP01S, and that means that the output is shown by the blue onboard LED. If your board is an ESP01, then you would need to add an LED and resistor to your circuit in order to be able to see this output. We'll now test the board's Wi-Fi capability. The ESP8266 Wi-Fi library is required, as are 2 variables containing your router's ID and password. In a later video, we'll look at making the project configurable remotely. This setup code initiates a connection with the router and waits for a response. The program does not proceed until a response has been received. Here we report a successful connection and show the IP address that the router has issued. Although the ESP01 only claims 1 dedicated input-output pin, in fact TX, RX and GPIO0 can all be used for extra input-output tasks. For this project, GPIO0 will be used for manual input. This is useful because we already have a button for it, although there is a potential issue that if both buttons are made available for the end user, it will be possible for them to put the project into flash mode. The first 2 variables here will track the status of the GPIO0 button. The third will turn the loop function into a timing loop. In the Arduino setup, the loop function runs continuously to perform the tasks that the project needs to do. The ESP01 runs at 80 MHz, so the loop function is running extremely frequently and extremely quickly. The program will break that down and only test the GPIO0 pin every 100 loops. The incoming button press will act to toggle the output because there's only 1 button. The swdbounce variable will be set when a key press has been processed and will prevent any further processing until the button has been released. Here I'm adding some very basic web capability to the program, starting with the HTTP server library and the creation of a web server object. Some setup code creates handlers for the root page and the page not found error condition. On the ESP8266, page handlers are implemented in code. Then the web server process is initialized and the program is now able to handle incoming requests for pages. Handling individual page requests is simply a matter of creating a function that returns a relevant response. Here we're creating a very basic page that simply tells us the status of the GPIO2 output. But I'm creating the HTML headers for scripts and styling that will be used later. For simplicity, I'm just concatenating the page text together using a string variable. There may well be a more efficient way to do this. Here, the program adds conditional content to the page depending on GPIO2. This is the most basic way to make web pages provide information about the status of the module. Using the IP address noted earlier, we can now test the changes, downloading them to the board in flash mode as before. The page responds to manually changing the output, although as written here, it can only show changes to the output when the page is manually refreshed. It also seems relatively slow, which is probably because the whole page is fetched on each refresh. Over the next few videos, we'll complete this project using these 5 add-ons. Future projects include a red LED retro atomic clock, a home automation hub that will allow multiple time switches to be connected together and operated via infrared remote control, an Amazon compatible power switch, and what could very well be the world's cheapest computer. If you've enjoyed watching this video, don't forget to like, subscribe, or leave a comment. If you've got any suggestions about future projects, please make a note in the comments. And don't forget to hit the bell icon to receive notification of future videos.